get started on time. I'm sure people will be happy with that. This is going to be a continuation of the EoR theme, at least EoR adjacent. So we'll get started here with Shintaro talking about drift scans at ultralow frequencies.
Okay. Thank you very much. Hello, everyone. Can you hear me? I think so. I'm Shintaro Yoshira, postdoc at NLJ Japan. Today, I would like to give some reports about our progress of analysis of the MWA drift scan ultra-low frequency data. This is a kind of a collaboration with many students from Kumamoto University. So let me start from the motivation of this work. We are starting this work because we are really far from the cosmic dawn power spectrum still. So this is a summary of the power spectrum, which has been done, the x-axis is the redshift, y-axis is the power spectrum, and you can see lots of kind of arrows, which is the upper limit from lots of instruments, including MWA, and as reported in the morning sessions, the MWA finally gets MWA is a kind of one of the leading instruments for the upper limit at EoR. But actually, the MWA is also leading the upper limit at the cosmic dawn power spectrum, you can see here. But still, the expected Tellurian signal from the cosmic dawn where the first star has formed is roughly 100 millikelvin squared, but the upper limit is 10 to the 7 or something. So we're still really far from the expected signal. And another motivation is the edges. I don't know if you have heard about edges, but the edges is a instrument for 21 centimeter global signal, and which reports really strong absorption line at redshift 18, roughly. The amplitude is roughly 500 millikelvin, but no standard cosmology can explain this very strong absorption. So many theorists try to make some new model to explain this really strong absorption line, but some of the model also predicts to explain the edges results 10 to the 5 millikelvin squared per spectrum at redshift 15 or something. So to validate the edges result, which might be changed the cosmology, we are also working on this data analysis with the MWA. And but the problem is not the sensitivity, because the MWA has enough sensitivity to test the edges result with just a few hours of the integration time. But the problem is the instrumental systematics. So here the right panel shows the my 2021 paper. Here is a noise level, expected thermal noise level, but this is what I measured in the 4 years ago, and you can see here huge gap here. This is due to the power spectrum is limited by not thermal noise but the systematic errors. So we need to understand more carefully about the ultra-low sky. So we took roughly 90 hours of data. Sorry, this is just a handmade mosaic image, so you can see here some gap around here. But this is an ultra-low sky at 85 megahertz, and I took roughly 90 hours of the data, and which operating the frequency from 74 to 105 megahertz using the compact array mode. And all the observation is done with the drift scan, fixing the beam to mitigate, to cover the wide range of the sky. So again, okay. So the goal of this project is kind of understand more carefully about the ultra-low frequency sky. So let me quickly mention about the calibration. So I use the Billy and hyperdrive, and the Billy for processing and make some flagging information, and run the hyperdrive for direction independent calibration with a baselines longer than 20 lambda, and using the latest version of the radio catalog, basically developed for the EoR community. Yep. Oops. So let me introduce first the visibility amplitude as a function of LST. So here the x-axis is LST, y-axis is the visibility amplitude. Different color indicates the bin of the different lengths of the baseline. So I calculated, for example, the cyan line indicates the averaged visibility amplitude of the baseline of roughly 15 meters. To visualization, I scale up each line, but the solid line is a low data, so before the calibration, and the dotted line is a model calculated by using the hyperdrive. And first of all, you can see here, for example, the baseline longer than roughly 100 meter. The model will explain the low data sky. So without calibration, because the MWA is a really stable and decent instrument, the model can also predict very precisely at the sky. But you also can recognize around here, the very short baselines cannot be explained by the model because we don't have a diffuse emission model in the data, in the source list. And also, one who mentioned here's a huge gap, deep or mountain or something. Actually, this is completely dominated by the Fornax-A because the Fornax-A is roughly 3,000 Jansky sources at this frequency. So, yeah, this is from this amplitude visibility distribution as a function of LST. We presumably the region around here, maybe the kind of best sky for further deep observation. But we still working on these topics as well. And also, I will also mention the at the LST less than 0 degree. Some of the baselines are dominated by diffuse emission. So presumably 20 lambda threshold for the DI calibration may be risky because it can cause some signal losses. But anyways, I calculated a two-dimensional power spectrum at each directions. It's kind of difficult to distinguish which one is the best field. But based on the dynamic range estimation, dynamic range means I compare the lowest K perpendicular, K parallel mode power and the power in the EoR window. And high dynamic range is achieved at the direction of light ascension of 50 degree. This is because the previous one, this power spectrum is calculated by using just 5 minutes of the data. Then the power spectrum is limited by not thermal noise, but actually limited by the error on the gain calibration, because we get a gain solution at each fine channels, but if it has some fluctuation as a function of frequency due to the low SNR, it makes some fluctuation in the spectrum of the foregrounds, and which easily dominates the EoR window, which is introduced in the morning sessions. So here is the x-axis is LST and y-axis is a gain error, and at each several coseband channels, and you can see some behavior. This is so from this figure you can see some and the gain error is the minimum at the direction of roughly 40 or 50 degrees because we have Fornax-A. So Fornax-A is really bright sources, but which is bright source, bright foreground, but it's available for the decent calibration. That's why I got to make a higher dynamic range at this direction. And actually, to investigate the edges or the fiducial 21 centimeter model, we need more than 1 or 2 orders of magnitude better calibration accuracy for detecting the 21 centimeter signal. To overcome the difficulty, we are now trying to get some averaging the gain solutions to reduce the gain error using the moving average method. And because we are also at some point, the gain error will be dominated by the not noise, but the miscalibration error, because we don't have a perfect sky model. But we are doing the drift scan. So drift scan essentially observing the independent sky. So presumably the gain error caused from the mismodeling is independent at each direction. So we try to make we assume the instruments are very stable as a function of time and calculate the moving average and try to understand what's going on. And Takumi Ito, PhD student in Kumamoto University, has tried to understand what is the requirement to detect a 21 centimeter signal with a Madsen white filter using the simulation with the hyperdrive. And we found presumably 100 millijansky sources must be taken into account for the calibration, or we can't detect the 21 centimeter signal at the 100 millikelvin square things. And also, actually, the gain solution changes day by day sometimes because we have ionosphere at this frequency is really ionosphere really strong. And well, first year master course student Shiori Oguro has investigated the ionospheric activity using the hyperdrive. Here, the x-axis is the time of the observation. The y-axis is the median offset of each radio sources within the field of view, and different color indicates different days. But she has already found some interesting behavior here. Okay, thank you very much. And we are investigating the what kind of ionosphere activity causes this outlier behaviors. And also, at this frequency, we need to take account. We think about the RFI because it covers the FM radio. And well-done PhD student in Kumamoto University has found the gain, even after the EoR flag RFI flagging, we still have some faint RFIs, but it kind of RFI could biases the gain calibration solutions. But based on the the biased gain is also available for the RFI detection. So we've done try to identify the visibility or tiles which dominated by the RFI, and he achieved the 30% of the improvement in the power spectrum. And also in terms of the RFI, we can't ignore the moon as well. So moon all the time reflects the FM radio from the Earth, from any countries, because FM is too bright. This is led by Daiichi Nagakura, first year master course student. He identified the moons in the radio images, tried to measure the moon spectrum at this frequency. And you can see here actually maybe too small, but actually, the flux density of the moon reflected FM is roughly 20 Jansky or something, and the spectrum is not smooth at all. So it's easily make some unwanted structure in the EoR window, and he now trying to detect the kind of structure in the actual data. And also, machine learning technique could be available for identifying some outlier dominated by the RFI or some unwanted structure. This is also led by the Teppei Morimoto, first year master course student. We are using the VAE, which essentially try to identify the kind of a particular or important parameter based on this machine learning technique. And we have already detecting some outliers in the visibility. So this is basically, we are trying to find some outlier at each 8-second visibility spectrum. So, and actually, I have already found some unknown outliers in the data. This is the left panel shows the delay power spectrum. X-axis is a delay or K perpendicular. There were K parallel. Sorry, Y-axis is the power spectrum. This is a redundant baseline, so each visibility must be identical to each other, ideally speaking. But some red and blue shows some outlier behavior. And if I check the visibility spectrum, the blue and red line shows some unwanted, very strong structure. But presumably this is RFI because I couldn't find such kind of structure in the gain solutions. And this is a kind of a current upper limit from the MWA ultra drift scan data. Yeah, the one-dimensional power spectrum in units of millikelvin squared. The x-axis is the wave number. The y-axis is the power spectrum. Here, the black line is the upper limit I have detected 4 years ago. And currently, all power spectrum at each sum of the directions are more or less consistent with the previous analysis. Although I didn't perform perfect optimization for the data selections, but you can also find the EoR, the green line corresponds to the power spectrum at the direction of light ascension of 0 degree. This is the EoR 0 field. Has some little bit stronger power here, but it reminds me this outliers actually. So I try to remove the some outliering power spectrum things, and I got this upper limit. So from this results, it's difficult to see. Currently we have a kind of upper limits well consistent with previous work, but we are now trying to get a better upper limits by using data selection based on previous, based on the work I previously introduced. So this is a kind of a summary. We are doing some MW ultra data analysis for understanding the 85 megahertz of the sky. There are a lot of things to do. This is not limited in the list, but and also I also want to finally mention about MWA phase 3 because this is a MWA phase 3 project meeting, I think. This is a phase 3 result. Thanks to Dev No. Dev provided me the UV fits file, and I calibrated with the hyperdrive latest version. So yeah, so I would like to say phase 3 is best. I mean, this is a phase 2. You can see lots of very strong spherical, the Cosband harmonics is better in the phase 3. Although this is just a 2 minutes of data, presumably we could see some other systematics below the noise level, but clearly the MWA phase 3 can easily detect the edges model, presumably. So I'm really looking forward to use this phase 3 data in the upcoming 5 years. Thank you very much.
Right, thank you for that. Do we have any questions from the room or anywhere?
Oh, hi. I very much like your use of drift scans because that avoids lots of errors when you try and do electronic tracking. So that's good. Now, you started motivating it by saying you at least want to see if you can exclude the edges result. Mm-hmm. Edges is global. So there's a complete range of angular scales from global to your shortest baselines.
Yes.
So why don't you just focus on that very short baseline, in which case ionospheric positional changes and details of the sky model don't matter?
Thank you very much. Even for the shortest baseline for the MWA, it has some not correspond to the size of the beam of the edges. But at the shortest baseline, we have galaxies. Lots of galactic synchrotron radiation make more than 2 or 3 orders of magnitude stronger than other frequency, other wavelength, other baseline length scales. So presumably we need to more accurate gain solutions to overcome these high dynamic ranges. So that's why presumably the baseline around 50 or 100 meter is much better for identifying the tornado, I think.
But if you're trying to test edges, it's not sensitive to those structures.
No. I mean, I don't intend to directly detect the edges global signal because I just want to detect the model which predict the small scale fluctuation, and the model is inspired by the edges result. So we need a kind of a small scale structure, small scale resolution, and this is a kind of so edges result is basically get the very large scale information, but we also can test the small scales to this is important to validate such kind of extraordinary models, I think. But yes, I can discuss even later, I think.
Right. Any other questions? Comments? Yep. Dev over there.
I don't know how I can start.
Thanks, Yutaro. Could you go back to the plots you've got of the power spectra that you had comparing all the LSTs and then comparing to your one in black? Yep. Okay. What's with the peak at K 0.03? Sorry. Why is 0.03 bigger than 0.01?
0.03 is bigger than 0.01. You mean
yep.
Here and here?
Where your mouse is?
Because I applied a K cubed.
Ah, cool.
Yep.
Thanks.
time for one more very quick question or comment. No? Alrighty. Cool. Thank you very much again, Shintaro. And now we've got Randall talking about, I believe, M-mode imaging.
Oh, no, that's not right. Is it just right? Oh, okay. Looked up and that wasn't you.
Giving away my reveal.
Sorry.
All good. Okay, yep. Yep, hi everyone, I'm Randall Waith. I'm giving this talk on behalf of Jayden and the small team that you see there for the very good reason that you've just seen that Jayden is a new dad. So congratulations to Jayden and Chantel. Last we heard all was going well. So I'm happy to give this talk on his behalf and hopefully can do it justice. So this is about making all-sky maps with interferometers, and in particular combining data from two different interferometers, one of which we all know and love and one of which you might not know so much about. And well, here we go. So motivation, I mean, this is an EoR adjacent session, and the motivation for this is, you know, EoR and a whole bunch of other things. So all-sky temperature calibrated maps are incredibly important across a whole range of astrophysics, but they are very, very important for EoR and low-frequency radio telescopes. They form the basis of the sky model for working out the telescope sensitivity and all that sort of stuff, and they form the basis of the foreground model for EoR. So we need maps, and the one that is sort of the workhorse that's been around for 4 decades now is the Haslam map and its derivatives, which have been extrapolated down to lower frequencies. And this is a genuine all-sky map. And yeah, as you can see, so 1,300 plus citations, not bad for an all-sky map. But we need ones that are at our frequencies, and we also need ones that are, you know, maybe have other features like polarization, and we need ones that don't have the systematics in it that the Haslam have. So it's time for some more all-sky maps at lower frequencies, and that's what this work is all about. The way we're doing this is completely different to how we normally do interferometry that you're probably all familiar with. We're using spherical harmonics and transit interferometry, which I'll explain in a second. But just quickly about spherical harmonics, they are they are the basis function for describing functions on a sphere. They are analogous but not the same to Fourier components. And you can see that a spherical harmonic coefficient has sort of 2 parameters, an L and an M, which are unfortunately have nothing to do with the L and M's of image space maps. Okay, they're completely different L and M's. And the components of the L and M coefficients, just like in sort of Fourier modes, build up the sky on certain angular scales. Okay, so what we're aiming to do is to get measurements of all of these modes, which we can then use to make a nice image. So hopefully you've all been sufficiently hypnotized by this animation. Okay, so how do we do this? So as I said, we're talking about taking data with an interferometer, but we're not tracking the sky. So we're interferometer, we're phasing at the zenith, we let the sky drift past as a transit instrument over a sidereal day. We take the visibilities for that sidereal day and then we can Fourier transform them, which sounds weird, but you can do it. And it turns out, I'm going to spare you the maths, but it turns out that there's a very, very nice relationship between the Fourier transformed visibilities, which are these M's, okay, and the M's that are in the spherical harmonic coefficients here. So sparing you all of the maths, you can then write down the problem of the relationship between the measured M modes, the Fourier transform of the visibilities, and the spherical harmonic coefficients as a beautiful linear algebra equation. So once you've done that, no problem, right? Just invert the matrix, easy, off to the pub. Okay, so that's the basic idea. I think it was either discovered or probably more likely rediscovered in 2013 by Shaw et al, and then it's been used by a few group since, including my former PhD student, Mike Creel, who I think presented his maps using this technique at some previous meetings. Okay, so as I said, the idea here is M-mode interferometry. It is not map making, it is not mosaicing. There are no W terms, there are no regridding or any resampling or anything like that. You're going directly from 24 hours of data to an image of the sky. Okay, the downsides is it's computationally expensive. You don't get to use any of the shortcuts that we know and love in normal interferometry. But the goal here is to make an all-sky map, or at least as much all-sky as we can see from here, and build this foundation for this moving forward. And as I'll say in this talk, this one's actually combining data from two separate telescopes. So the previous map that Mike Creel showed was a nice all-sky map made with the EDA2, which is SKA prototype system run by Curtin. And so it's an SKS station just with MWA dipoles. It's obviously got a lot of baselines. Maximum diameter of the station is 35 meters. Okay, the goal here is to combine data from this station with the core of, excuse me, the MWA that we all know and love, to make a map that's better than what either one of them can make on its own. So all of the short baselines and the longer baselines all combined together. And one of the beauties of this technique is that you can combine data sets from different telescopes, and it all just goes into that beautiful linear algebra equation, and you just invert it and it all just magically works. So the one caveat here is that in order to match the resolution of the individual dipoles of the EDA, we're turning off all but one dipole in the MWA tile. So we're just using a single dipole in each MWA tile, using the core of the MWA, and we get these baselines here. So we've basically got two separate arrays taking data at the same time. We're not cross-correlating them, but we're taking simultaneous data, which gives us two sets of visibilities of different scales, with one single antenna looking at the sky over the day. Okay, so because the data are taken at the same time but independently, step number one is to rescale the data sets to be on the same flux scale. Thankfully, that one's fairly straightforward. I won't dwell on it too much. Because there are so many baselines in the EDA2, you can find matching ones in the MWA that are almost identical, and then you look at the visibilities and you rescale so that they're both on the same scale. So this is something Jaden did pretty early on and got this all sorted out. So I won't dwell too much more on that. Right, so once you've done that, you can then start making maps of the sky. So the first map you can do is make an image just with the EDA2 data. So this is similar basically to what Mike would have shown in previous talks. The catch is that when we did this back with Mike, we actually took two data sets separated by 6 months, imaged both of them, and then weighted mosaic them together to get rid of the sun. Unfortunately, when these data sets were taken, we tried the same thing, but on one of the days that we took the data was the biggest solar flare in this solar cycle. So it absolutely wiped out the data. Great data if you're a solar physicist, but not so good for M-mode. So what we are left with is one day where there is the massive sun in the data set here. And dealing with this has actually been a big part of what Jaden has been trying to deal with. So we need to deal with the sun, and then we need to try and combine the data sets together. So that's where we're going. So there we go, sun subtraction part one. Yep. Okay, so basically I'll go over this fairly quickly, but basically the sun is so incredibly bright that the only real practical way to get rid of it was essentially peeling it on the shortest time scales of that were available in the data. And that meant recentering for every single time step, recentering a beam on the sun, measuring its offset, measuring its apparent flux density, and trying to subtract that out from the data. So This was quite challenging. There were small offset sets. There's, hotspots on the sun that can change its apparent center and so on. It makes it tricky. But basically, without going into too much details, Jaden sorted out how to do this using post-correlation beamforming. This is the actual data with all these little mini solar bursts and things in it. As I said, basically peeling at the finest time resolution of data in the data. And then the same thing again with the MWA. So it's interesting that the shape of the MWA beam is not so clean as the EDA2 beam. But what you get when you subtract out your model from the sun is these nice residual visibilities, and these look pretty much as you expect, given if the sun wasn't there. So this is subtracting the sun from the MWA data. You get the nice visibilities at the bottom there. Same thing, subtracting the sun from the EDA2 data. Nice residual visibilities at the bottom. And it does an amazingly good job of getting rid of the sun. So this is the EDA2 again with the sun in it, and this is with the sun gone. And it's really impressive. Actually, there's some really faint sources that are actually real that have popped up. So that's great. Jaden put a lot of work into sorting out how to do this. Seems to have worked really, really well. So the goal now is to combine the two data sets. Oh, and I'll just quickly show as well that you can see in the magnitude of on the left-hand side there, that shows the sort of the magnitude of the spherical harmonic coefficients. And so you can see how much power there is in the sun there. It's just really, really dominant. So this then is getting to what we're actually trying to do here, which is to make the better quality sort of a Haslam map scale, angular scale map of the sky by combining the two data sets. And you can see now, if we look at the spherical harmonic coefficients, we've got higher angular modes that come from the longer MWA core baselines. And the image itself clearly has finer angular resolution, which is great. Maybe I'll just flick back and forth between these a couple of times. Yep, so that's the EDA, and there's the MWA. So you can see lots of those nice little A-team sources and things are becoming more well resolved. And you can also see that this is a dirty map, okay? So there's a certain amount of deconvolution here that is unavoidable. So we need, that's the current problem. But even for a dirty map, this is looking pretty good. You can see there's pretty clear side lobes. They're kind of the equivalent of the synthesized beam side lobes in this map. Okay, and this is what it looks like in the sort of, I'll say native equatorial coordinates. Since we're dealing with the sky rotating around, this is what we're really looking at. And you could be forgiven in the previous plot for thinking these this blob here is side lobes of the galactic center, but it's actually not. These blobs here are actually side lobes of our good friend Cygnus. But the thing is that they're completely predictable. And so by cleaning the compact source out of this, you actually do deconvolve these side lobes as well. It's just one of the weird, slightly non-intuitive artifacts of the way the M-mode imaging works. So we can look then, okay. So one of the thing that Jaden's been working on most recently is cleaning. So he's just looking at a sort of a fairly standard clean algorithm, identify peaks or features or whatever you want to model them as, and then subtract them out from the image. So the good news is that this actually seems to be working really, really well for the EDA2 image. I'm almost done. The EDA2 image. So this is a nice cleaned EDA2 image. You can see all of those side lobes are gone. All of the large scale structure is really, really nicely represented. We've got, I guess it was restored here. So Cygnus has been restored. And this is looking really, really good. The catch is the cleaning for the combined data set, so the equivalent of this one, is not going quite as well as planned. So unfortunately, what I'm going to have to do is leave you on a bit of a cliffhanger because Jaden the baby arrived before he got this sorted out. I'll go to the summary and maybe I can, if we've got time, I can show you another couple of images. But the current goal is to sort out how to do the cleaning with the combined EDA2 and MWA maps. It's almost certainly a sort of a weighting type problem. But once that happens, we should get a really, really nice sort of Haslam scale map out that will be, you know, a genuine sort of contender for Haslam in the Southern Hemisphere. So what's he done? He's demonstrated multi-system M-mode pipeline. So this is combining data from two different telescopes together. This naturally can be done with the M-mode formalism. You don't have to do anything special. You just put it into the sausage machine and crank the handle. With the help of Jishnu Thekapatu, who's also recently moved to Cairo, they've created a really nice pipeline that's really quite fast now, so they can do the inversions and imaging quite quickly. And he's currently working on this clean algorithm that will sort out the combined EDA2 and MWA data for this this beautiful oil sky map. So I'll stop there. Thanks.
Cool. Thank you for that. Do we have any questions? I see a question back there, but I actually can't see who it is because it's too dark for my eyes.
Hey, Randall. Is this working? Yeah. I feel like I've forgotten something or missed it in your presentation, but can you say something about how the antenna response pattern fits into this? I mean, at any given moment, you're not observing the sky, you're observing the sky times the beam.
Yep. I completely glossed over that. It is in this, it's in this equation. Okay, so, all right. So going into the next level of detail, as part of forming this design matrix, you need to decompose your beam pattern into spherical harmonic coefficients, and then they go into this B term. These are the beam, what does he call them? Just the beam, beam fringe pattern or something or another like that, yeah. And they go into that beam, that B, and hence that comes out as part of the inversion. So it's a good question. You need to know your beam pattern to go into this properly, otherwise the inversion is obviously not going to work. But that being said, as long as you know your beam pattern, they don't have to be the same beam patterns. Okay, so in principle, you could have you know, slightly different ones for the MWA single dipole tile and the EDA, or any other telescope which has a different response. As long as you know that response, it goes into that equation. Yep.
Okay, we have, I think, 3 hands there, but I saw Alex first, so we'll go with that.
Thanks, Randall. I ought to give a little bit more detail about how you're going about the absolute calibration, so getting the final maps in Kelvin equivalent to Haslam.
Well, because it's an interferometer, we can just calibrate it normally, which is great. So we don't need anything else like that. We can just calibrate with our favorite A-team source or whatever else we want to use, and it's pretty straightforward. Yep.
And Divya, do you have it? Yep.
Can we get the solar data here?
Solar data. Sure. Yeah, absolutely.
So yeah, I'll talk offline.
Yeah.
Thanks. Yeah.
Happy for it to go to a good home.
One person's trash.
I believe, Ron, did you have a...
Will you be able to straightforwardly use this technique on the Escala antennas?
Yeah, I mean, as long as you know the beam, you can use it for sure. And thankfully with the Scalas, a huge amount of effort has been put into simulating those beams for sure. So yes. Yep.
Okay, we've
Right up the back.
one more at the back there, right below the light that I can't see very well.
It's AJ.
Thanks, Randall. So the plan is to replace Haslam with a new EoR sky map, right?
Yeah.
So what are the plans for the northern skies?
Oh, I'm glad you asked. Did Jishnu put you up to that? So Jishnu is working on a partnership with one of the LOFA international stations with Tabera Karotsi and some of his staff. And yes, as I said, you can combine data from different telescopes with this, and they don't have to have the same beam. They don't even necessarily have to be observed at the same time, although it probably makes sense to do it. So that's exactly what Jishnu is doing. This is his work in progress. We're probably going to have the same sort of cleaning issues. But yep, the goal is a true all-sky map, a genuine all-sky map, and it totally can be done.
Alrighty, I think that is it for this one here. So we're going to move on to well, actually, sorry, applaud again. And then we'll have Nick.
Good afternoon. Well, I'm afraid I'm not going to have any baby pictures in this talk. The only babies might be baby black holes. So I'm going to be talking about searching for the first black holes of the MWA, and a lot of this work has been done in collaboration with AJ Hedge and Jess Broderick as well. And so what I have here is a picture of Gleam J0856, which is most distant radio galaxy we know above a certain luminosity, 10 to the 28 watts per hertz. And this was found by the MWA. So radio galaxies are beacons of the most massive black holes over cosmic time. So we're talking about billion solar mass black holes. These are hosted by the most massive galaxies. They live in the largest dark matter over density. So they're a trace of galaxy growth and structure growth over time. And the great thing is that the most luminous radio sources we can detect back to any redshift that JWST has probed, should they exist at those redshifts. So apart from studying the evolution of galaxies and black holes at early times, what advantages does radio have when finding these high redshift obscured black holes? Well, because most AGN are obscured at high redshift, looking for them in the radio helps find those obscured AGN. Of course, not all obscured AGN are going to be radio loud, but if the radio emission's independent of the obscuration, this will help provide a representative sample of what some of the earliest black holes look like. And of course, these radio galaxies are powerful jets. They impact their environment. And so what impact does that have on the galaxy growth and the growth of the environment around the galaxy over time? And of course, they can be a unique probe of the epoch of reionization. We already heard from Kath about how we can search for the 21 centimeter forest. This is a simulation from over 20 years ago of what the SKA might see of a redshift 10 source. I think this was an earlier, more sensitive version of the SKA, so we might not quite get data as good as this. But we can certainly search for this neutral hydrogen in the early universe, particularly if we get more and brighter candidates at high redshift. And of course, we can find the rarest sources. So an important point is that you've heard about JWST finding galaxies up to sort of redshifts 12, 14. These are over tiny areas, and they don't really find the massive radio loud sources that come from much wider searches. So you really need to use wide area searches to find these unique objects at high redshift. And this is a JWST targeted observation of a redshift 4 galaxy. So you have to target them. You can't find them in the deep surveys. So this is the state of what we knew about the high redshift luminous radio sources about a decade ago. So we have a compilation of luminous radio sources, and I've indicated the kind of luminosity range where Gleam will find bright sources. Gleam can push a little deeper. And so what we've managed to find over the intervening years with Gleam is we found 3 new radio galaxies that fill this redshift space. So one at about redshift 3, one about redshift 4, and one at redshift 5.5. And so this was the one I was talking about, which is now the most distant radio galaxy above a luminosity cut that we know about. The reason we made less song and dance of it at the time was that it was officially only the second most distant radio galaxy. But then this source here, TNJ 15 something, can't quite read it, got demoted. Follow-up observations realized that the original redshift was wrong. So Gleam now holds the title. Of course, there's been radio loud AGN found a higher redshift. Here's one from deep observations of the cosmos field, but it's far less luminous by orders of magnitude. So yes, it's probing well into the epoch of reionization, but it's nowhere near as luminous as the sources we've been finding. So the goal ultimately will be to find sources somewhere in between, objects above redshift 6, that are far closer in luminosity to what we know at redshift 5. So AJ already mentioned a bit about our selection technique, so I won't dwell on this. But basically, by looking for sources with curvature or steep spectrum, shift them to higher redshift, they're still detectable in MWA surveys. And we also look for sources that have faint optical hosts in K-band, and they're very compact because they're very young. And so this is the most distant one, Gleam J0856, discovered from ALMA scans, which identified these two CO lines. And it's actually unusually large for a radio galaxy at this redshift, being sort of at least 3 arc seconds in size, with a possibility of a counter radio jet there. So ongoing work is to try and establish, is this counterjet real, and what are the X-ray properties of this? It's very bright, should be able to detect the jet in X-rays as well. Then Gleam 0917, this is at redshift 3, not quite such an exciting redshift, but a very exciting source. For a long time we couldn't figure out what redshift it was, but this was nailed by HST GRISM observations. We got this bright 03 line and 2 fainter neon lines. So obviously we could work out the luminosity of this source. We could model the optical spectrum of the source, and we found it's got a very low star formation rate for its stellar mass for the redshift. We also, as AJ highlighted, the VLBI observations showing the 2 compact components making up sort of 90% of the flux of this source align very well with the green contours representing the ionized O3 gas. And so this strongly suggests that it's the jet that is propelling the gas forward and shocking it. And this is further confirmed. You don't really need to know the details, but the ratio of the optical lines suggests that the gas is shock ionized rather than photoionized. We can model the radio emission, and we find that this is a very young radio galaxy, so about 30 kilo years old, partly because it's very small, although it's very luminous as well, very powerful jet. And so the hypothesis here is that this young jet is quenching the star formation in this galaxy. So one of the big mysteries from JWST is, why do we find all these massive galaxies with very old stars in them? They had to form stars quickly, and that star formation had to turn off. And so you can run a back-of-the-envelope calculation, and all the massive galaxies that have star formation turned off, that star formation could have been turned off by very short-lived radio emission, say less than 100 kiloyears. So this is very intriguing. And then just highlight AJ's exciting result. He's found one of the most massive clusters around Gleam J0053 at redshift 3.88. He found 7 spectroscopic members through careful analysis of the ALMA data, and modeling of how massive this cluster could be suggests it will likely grow into the coma cluster by the time it reaches the local universe. And this particular radio galaxy, protocluster member, has a mass of about 10 to the 12 solar masses, which is incredibly large for a galaxy at redshift 4. One thing we can do is look at the masses of the black holes. Now, we haven't been able to probe the black hole masses directly, but because these objects are so radio loud, we can use energetic arguments to determine minimum mass for the black hole, assuming very efficient accretion and very efficient jet production. And we've overlaid the black hole masses as a function of galaxy mass for our radio galaxies, and we've compared them to known radio galaxies with direct black hole measurements and these little red dots that JWST has found. And all these galaxies tend to lie on the local relationship for giant ellipticals. So it seems that all these galaxies are going to evolve into giant ellipticals by the time they reach the local universe. Whereas this relationship, which little red dots are often compared to, is the one for active AGN in our local in the local universe. But of course, they reside in very different types of galaxies, much less massive than the massive galaxies we study here. We can also look at the many QSOs that have been found in radio, and there's quite a lot. There's a couple of blazars and a whole bunch of QSOs, and somewhere in there, I think this one, the downward triangle, is the source that Kath was looking at earlier. But you can see, this space is growing, and MWA plus LOFAR are constraining the radio emission from these AGN. So there's certainly scope to find something in this space up here. Just a highlight of one of the results from the QSOs. This particular radio galaxy detected both with Gleam and RAX down here, very radioluminous, but it's the most luminous X-ray source above about redshift 5.5. And the inference in this paper by Luca Hina was that this is a super Eddington accretion radio source, which is very exciting. And please don't publicize this. I think this will be a press release in a few weeks. So, as I said in the abstract, I wanted to look at the prospects for H1 detections. So I've started to do some very advanced modeling of what we might expect to see. This, of course, is a noiseless model, and I've been looking at in particular, J0856 at redshift 5.5. And so this is the prospects, what we might get with MWA phase 2 in 50 hours. And fortunately, this absorption features right at the edge of a coarse channel. So if you do the 80 edge channel flagging, as is common, you will lose this part of the spectrum. So this is where sort of MWA phase 3 will be very useful. We can also use slightly smaller channels. And with 100 hours, this is the kind of detection we can get. I should point out this is just in situ absorption by neutral hydrogen. We would expect probably intervening absorption as well at lower redshifts, higher frequencies. And then, of course, I just did a simulation of what we might see with the SKA. And so all I'm doing is just adding Gaussian noise to the model. So it bodes well for what both MWA and SKA can do. And I do have a student, master's student / honours student working on the MWA data at present. So we'll see how they do. And of course, we can have these be great targets for low frequency VLBI because we can look at the H1 absorption in both components as these very compact sources, and now give you even finer detail about the distribution of the neutral hydrogen. This is just showing the parameter space of our candidates. We've got many more extreme sources with very faint K-band infrared fluxes and very bright in the radio. This is the sensitivity that we're going to get from Euclid and LSST surveys, which will allow us to easily find the hosts of all these galaxies. So expect to see exciting results in the coming years once that data starts flooding through. I'm running over time, and so this is just highlighting the importance of interstellar scintillation. This plot's provided by John and showing that peak sources at high redshift will have scintillation indices of around 0.5, which is what we find for our bright sources. Yes, I think I'm on my conclusions. So MWA is already detecting radio sources well into the first billion years. Multi-wavelength follow-up is crucial, but upcoming surveys from Euclid and LSST will help find these host galaxies. And there's plenty of scope for H1 detection in the near future. We've got the sensitivity. We just need to start working on the algorithms and start cranking the handle. Thank you.
Thank you for that. All right, do we have any questions for Nick? I see Ron with a hand there.
So Nick, just a week ago with Elaine Sadler, we had a quick look to see if we could see the H1 absorption scintillating, because then you'd be able to get some constraints on the size of the actual absorption. And the answer is maybe with SKA, if you can convince them to implement a short enough time constant.
Okay, thanks for that. Yeah, that's interesting stuff.
Listening, George? Implement some SK stuff
Yeah, Stephen?
Why hasn't LOFAR cleaned up on this, or have they?
Well, they did find all these lower luminosity objects here. So they found some of the ones down here and some of the ones up here. But to get these ones, you need wide area, deep infrared surveys or targeted follow-up. And that's just hard to get until we have Euclid and LSST. Yeah, but LOFAR, yeah, it's probably people are working on this, I'm sure.
Any other questions? I guess I'll ask something.
Sure.
All of the current GLEAM detections, I assume that's all the original GLEAM survey?
Yes, all from...
Is there any work being done with GLEAMX or any benefit to doing it with GLEAMX to find anything else? I guess you're not going to improve things if you're looking for bright sources, but...
GLEAMX will be important in the radio spectra. So part of this selection technique depended on the radio spectra. So if you want to use that, having more accurate fluxes from GLEAMX, it will be very helpful. And also for doing the kind of modeling that AJ showed, you know, if you're combining this GLEAM with other radio surveys, if you can have more accurate fluxes, then you might, then you'll be able to combine it better with, say, the low frequency, low FAR data. And to go back to Stephen's comment from yesterday, you could compare different GLEAM epochs, you could look for variability. And as Kat knows from some of her work, you know, some of these sources that turn over do vary. And so that might be an interesting aspect to investigate as well.
Cool. Got Shintaro over there with a question.
Sorry. Yeah, thank you very much. You mentioned about the low frequency VAVI to detect the high resolution galaxies, high resolution radio loud quasars. My question is what baseline is required to properly identify the region?
With the VLBI?
Low frequency VLBI, yeah. I think you mentioned about the VLBI.
At low frequency, yes. Well, so I kind of went over that quickly, but so the radio image here is Australian VLBI, the LBA. So you've got a separation of about a half an arc second or so. So it'd be great to do this at low frequency, and then you could study the two components separately and look at the neutral hydrogen absorption in each component. So yeah, just scale I can't do the sums in my head right now. But yeah, probably at least Australia wide.
Alrighty, we're at 2:30 now, so I think that is the break. Yep, cool. So thanks, Nick, again, and thanks all the speakers for this session.
Thank you.